Welcome to Lesson 8, Second Order Linear Differential Equations. We're going to characterize higher order ordinary differential equations. We already talked about first order differential equations. Now we will discuss second order, third order, and so on differential equations. We'll see some of the properties of a second order linear homogeneous differential equation, and we'll make our first stab at solving constant coefficient ordinary differential equations and initial value problems. Here are some questions to be answered in this lesson. What is the order of a differential equation? How can we write a formula for the nth order ordinary differential equation, a general formula for that? How many solutions does a second order linear homogeneous ordinary differential equation have? And what will the general solution of that look like? And finally, how do we solve constant coefficient linear homogeneous ordinary differential equations and also initial value problems? Let's talk about the order of a differential equation. When we took a calculus course, we talked about first derivatives. That's a derivative that has order 1. The second derivative has order 2. The third derivative has order 3, and so forth. So to find the order of a differential equation, what we would do is find the highest order derivative in that ordinary differential equation, and that would be the order of the equation. If the highest order derivative, for instance, is a third derivative, then the order of the equation would be 3. It would be a third order differential equation. So let's first look at some examples of first order differential equations. We could have the derivative of y with respect to x plus 4 times x times y equals 4x. This has a first derivative here and no other derivatives, so this is a first order differential equation. This second example, we just have the derivative of y with respect to x again, the first derivative here, no other derivatives, so this equation is first order. If we look at this equation, we have a first derivative squared here, no derivatives over here at all. So the highest order derivative in this equation is just this first derivative. It's squared, but that square doesn't really matter when we are calculating the order of this differential equation. The highest order derivative is this first derivative, so this is a first order differential equation. This one would be maybe hard to solve. Here are some examples of third order differential equations. The third derivative of y plus 10 times y equals 0. 8x times the third derivative of y with respect to x minus 7 sine x times the second derivative of y with respect to x plus 10y equals 0. And some second order differential equations. Y double prime minus 7y prime plus 10y equals 0. This involves the second derivative of y here, the first derivative of y here. So the second derivative of y with respect to x, let's say, is the highest order derivative. In this equation right here, once again, this second derivative is the highest order derivative. Didn't necessarily have to have zeros on the right-hand sides of all of these equations. I could have had functions of x and y, and these would have still had the same order, as long as you didn't put any derivatives on these right-hand sides. Let's talk about the general form of an nth order ordinary differential equation. This is not that useful for solving differential equations, but for writing down an nth order differential equation if you just want to talk about it in general. We could have a function g here of n plus 2 variables. And that nth order differential equation can be written as g of the nth derivative of y with respect to x for the first parameter here, the n minus first derivative of y with respect to x for the next parameter, all the way down to the first derivative of y with respect to x, and y and x, g of all of these parameters equals 0. And this will give us an nth order ordinary differential equation. Any nth order ordinary differential equation can be written in this form, and we will see an example of doing this very soon. So here's an example of an nth order differential equation written in general form. Let's let g of a, b, c, d, and e equal 8ea minus 5b plus 7 sine e times c plus 10d minus 2e squared plus 4. So now, if we look at this equation right here, g of the third derivative of y, comma, second derivative of y, first derivative of y, y and x equals 0, let's see what we get. Okay, well notice that here the order of these parameters is a, b, c, d, e. So if we want to figure out what 8ea would be, that's going to be 8 times e, which over here is x, times a, which is this one. So we get for this 8x times the third derivative of y with respect to x. Then when we look at minus 5b, in this, the b is the second derivative of y with respect to x. So this term is going to be minus 5 second derivative of y with respect to x. Then if we look at 7 times sine of e, okay, that's going to be 7 times the sine of this last parameter, which is just x. So we get 7 times sine of x. And it's also multiplied by c, which is, according to this formula here, the derivative of y with respect to x. Similarly, 10d turns out to be 10y. Minus 2e squared is minus 2x squared, plus 4 is just plus 4. And this all has to equal 0. So what we see here is a third order differential equation. And we did it by looking at this formula up here and this equation, and we made the substitutions that a was this third derivative of y, b was this second derivative of y, c was this derivative of y with respect to x, d was y, and this e was x. So we made these substitutions into this formula up here in order to get this differential equation. Let's look at the general second order linear ordinary differential equation. We can write it in the following form. A function of x times the second derivative of y with respect to x plus another function of x times the derivative of y with respect to x plus another function of x times y equals f of x. a function of x. So these coefficients on the left-hand side, the coefficient of the second derivative, let's call that a sub 2 of x. The coefficient of the first derivative, a sub 1 of x. The coefficient of y, a function in this case, is a sub naught of x. So basically, the coefficients in this case are functions of x, perhaps. Constants will do too. These could be constant functions. And this is a linear equation. And we want to answer, why do we call it linear? Well, let's define L applied to a function y of x to be a sub 2 of x times the second derivative of y with respect to x plus a1 of x times the derivative of y with respect to x plus a naught of x times y. Then this L is a linear operator. It has to satisfy two properties to be a linear operator. The first one is that L of y sub 1 of x plus y sub 2 of x is equal to L of y sub 1 of x plus L of y sub 2 of x. So let's see what happens if we calculate this. Can we show that this left-hand side is equal to this right-hand side using this formula for L of x right here and properties of derivatives? So if we look at L of y1 plus y2, that's going to be a2 of x times the second derivative of y1 plus y2 plus a sub 1 of x times the derivative of y1 plus y2 plus a naught of x times y1 plus y2. Now let's remember that the second derivative of the sum of two functions is the second derivative of the first function plus the second derivative of the second function. And similarly, we have a formula for first derivatives that looks quite a bit like this. Okay, so with that in mind, we look at this right-hand side, and this first term over here, a sub 2 times the second derivative of y1 plus y2, that's equal to a sub 2 of x times the second derivative of y1 plus a sub 2 of x, second derivative of y sub 2 of x. So this second derivative is here plus here. Then we have a sub 1 times the derivative of this sum. And here, using that property of derivatives, we have a sub 1 times the derivative of y sub 1 plus a sub 1 times the derivative of y sub 2. And then going on to the next term, a naught of x times y1 plus y2, we can just use the distributive property for multiplication here. And so that's going to be a naught of x times y1 plus a naught of x times y2. Now, we look at these first few terms in blue and recognize that as L of y1 of x. And these terms over here in, I guess, the dark red are L sub y2 of x. So what we have done is we started with L of y sub 1 plus y sub 2, which equals this stuff, which equals this stuff, which equals L of y1 plus L of y2. So we've shown that this first property holds. And we still have one more property to go to show that L is a linear operator. Secondly, we want to show that if C is a constant, then L applied to that constant times y of x is equal to that constant times L of y of x. So let's just start with L of C times y of x, go through some calculations to show that that is equal to C times L of y of x. Well, once again, we're going to use a property of first derivatives and second derivatives. I've shown the property for second derivatives here. The second derivative of a constant times y of x is just equal to the constant times the second derivative of y of x. So let's see how we can use this and other properties to show that this stuff here equals this stuff down here. So L of c times y of x, according to our definition of L, is a sub 2 of x times the second derivative of c times y of x, plus a sub 1 of x times the first derivative of c times y of x, plus a naught of x times c times y of x. And then, using the property that we can pull these constant multiples outside the derivatives, we can write that as c times a2 second derivative of y with respect to x. So this first term here simplifies or expands to this. Using similar property for first derivatives, this term here with the derivative with respect to x of c times y of x turns out to be c times that a1 times the derivative with respect to x of y of x. And then we have this term here, pulling out the c. So now each of these terms has a factor of c. We factor it out, so we have c times this plus this plus this. And then we notice that this stuff inside the braces is just L of y of x. So we have that L of c times y of x equals c times L of y of x. Much later, we will look at the homogeneous second order linear equation in more general form, but right now we're going to just look at an equation of this form. It's second order, since the highest derivative is the second derivative right here. The leading coefficient I'm going to assume is 1. If it's something else, we can divide through by the coefficient to make the coefficient here a 1. So we're going to look at the second derivative of y with respect to x plus the function p of x times the first derivative of y with respect to x plus q of x times y equals 0. This will be called a homogeneous equation because we have 0 on this side. If we replace this 0 with a non-zero function f of x, then this equation is a non-homogeneous ordinary differential equation. So for example, down here, this first equation is a homogeneous equation, ordinary differential equation, in the function y is a function of x. The second equation, where we have, for instance, the second derivative of x with respect to t minus the function of t times dx dt, and so forth, this is a differential equation involving the function x of t. So now we're going to narrow our focus down even further. Let's look at a second order linear homogeneous constant coefficient ordinary differential equation. It'll be a constant times the second derivative of y with respect to x plus another constant b times the derivative of y with respect to x plus c times y of x equals 0. We don't have a leading coefficient here of 1, but since these are constants and this is second order, we know that this a here is not 0, because if it were, this term would just be the 0 term, and we would really have a first order equation. So we're assuming here that a is not 0. We could divide through this equation on both sides by a, and we could get a second order linear differential equation, homogeneous equation, with a leading coefficient of 1. But in this case, we'll just look at it with a leading coefficient of a. It won't cause any problems. So this is a homogeneous differential equation in the form L of y equals 0, where L is a linear transformation or linear operator. A, B, and C, remember, are constants. For instance, it could be 2 times the second derivative of y with respect to x plus the derivative of y with respect to x minus 3y equals 0. That would be homogeneous. Another example would be something like this. Second derivative of y with respect to x plus 4 times y equals 0. These are both second order linear homogeneous constant coefficient ordinary differential equations. So let's see how we can solve a second order constant coefficient homogeneous linear differential equation. For instance, let's look at this problem. Solve a times the second derivative of y with respect to x plus b times the derivative of y with respect to x plus c times y equals 0. Here we're thinking of y as being a function of x. So here's what we'll try doing. We'll look for a solution y equals e to the rx, where r is a constant. So we're going to look at functions of x, solutions to this differential equation up here, that are exponential functions of x. Here r is a constant. It seems that this idea of using this exponential function to help solve this differential equation was due to Leonid Euler, but not quite certain about that. So anyhow, if we let y equal e to the rx, we have to calculate in terms of this what the derivative of y with respect to x is, and also what the second derivative of y with respect to x is, and then plug those into this equation and see what happens. So if we differentiate this with respect to x once, we have the derivative of y with respect to x equals r e to the rx. If we differentiate again, the second derivative of y with respect to x is r squared e to the rx. So we substitute those into this differential equation right here. And for this first term, we have a times r squared e to the rx. This second term becomes b times r e to the rx. This third term becomes c e to the rx, and so that has to equal 0. So we're hoping that we can find a function e to the rx that makes this true for all x. Well, if you look at this, every single term has a factor of e to the rx in it. Let's factor that out. So we have e to the rx times the quantity ar squared plus br plus c equals 0. Well, e to the rx is never 0. E to any real power is not going to be 0 ever. So that forces, if we want this to be true for all x, that forces the second factor to be 0. So r has to satisfy this equation, ar squared plus br plus c equals 0. This equation is called the characteristic equation of this ordinary differential equation. So let's look at this characteristic equation a little bit more. We're still considering this ordinary differential equation, constant coefficients a, b, and c, and we saw that the characteristic equation was ar squared plus br plus c equals 0. We got this by looking for solutions of the form y equals e to the rx. Well, this is a quadratic equation in that variable r, and we know for a quadratic equation like this, there are 3 cases we must consider. Let's call case 1 the case of 2 distinct real roots, r equals lambda 1 and r equals lambda 2. We'll cover later case 2 where we have one real root of multiplicity 2. It's a repeated root, in other words. And case 3 we'll consider complex roots of this quadratic equation, r equals alpha plus or minus I times beta. We're going to cover case 1 in this lesson, and we'll cover cases 2 and 3 in a later lesson. What we will see in case 1, where we have r equals lambda 1, r equals lambda 2, being two distinct or different real roots, we'll find out that there are two linearly independent solutions, e to the lambda 1x and e to the lambda sub 2x. And we'll then try to find what solutions we can get by looking at c1 e to the lambda 1x plus c2 e to the lambda 2x. By the superposition principle, if we have two different solutions to this differential equation, this linear homogeneous differential equation up here, the superposition principle tells us that if we take a constant times one solution plus a constant times the other solution, this will also be a solution to this differential equation. So let's look at an example of the characteristic equation having two distinct roots. So, real roots. So let's solve this homogeneous linear differential equation. 2 times the second derivative of y with respect to x plus the derivative of y with respect to x minus y equals 0. So we'll look for exponential solutions. So let's let y equal e to the rx. Then the characteristic equation of this differential equation up here is 2r squared plus r minus 1 equals 0. This 2 times the second derivative of y with respect to x results in our getting the 2r squared here. 1 times the derivative of y with respect to x here ends up giving us plus 1 times r in the characteristic equation, and minus y here, minus 1 times y, gives us a minus 1 here. So, and then we have equals 0 on the other side. So going from this constant coefficient differential equation to the characteristic equation was pretty easy. Well, let's solve this equation. We have many ways that we can try solving this. We could try to factor it, or we could use the quadratic formula. Well, in this case, it factors pretty easily. It factors into 2r minus 1 times r plus 1, and that obviously then has to equal 0. Let's just check this. 2r times r results in 2r squared up here. Minus 1 times r plus 2r times 1 gives us an r here, and minus 1 times plus 1 results in the minus 1 we have here. So if we multiply this out, we can see that it does equal what we have up here. These two equations are equivalent. Well, once we have it factored, set this first factor equal to 0, 2r minus 1 equals 0, and we get an we get a characteristic value of 1/2. A solution to the characteristic equation, lambda 1 equals 1/2. If we set r plus 1 equal to 0, then r in that case will be minus 1. So we have two solutions to that characteristic equation. R equals 1/2 and r equals minus 1/2. We'll call those lambda 1 and lambda 2 for convenience. So we get two solutions. From this value up here, we get y sub 1 of x is e to the half x, and from this value here, we get lambda sub 2x equals e to the minus 1 times x, which we can write as e to the minus x. So we have two distinct functions here, both of which satisfy this differential equation. It turns out that these are not the only solutions. This differential equation actually has an infinite number of solutions, as we will see later. So later we're going to cover the superposition principle, and that will allow us to find even more solutions to this differential equation. In fact, we'll find an infinite number of solutions. So quite a few functions are solutions to this differential equation, but obviously not all functions will satisfy this differential equation. So we have to find later the set of functions that satisfies this differential equation. We're about halfway there right now. So here's the superposition principle. Let's let L be a linear transformation, similar to those differential operators that we saw earlier. If L of y1 is equal to 0, and if L of y2 of x is equal to 0, so L of this function is the 0 function, L of this function is also the 0 function, then L of c1y1 plus c2y2 also is the 0 function for all choices of the constants c1 and c2. And the proof is the following. Look at L of c1y1 plus c2y2, and by the linearity of L, we can write this as L of c1y1 plus L of c2y2. But then, also because L is a linear transformation, we can pull this constant factor c1 outside, and we can pull this factor c2 outside this one. And so this stuff equals c1 times L of y1x plus c2 times L of y2x. But L of y1x is 0, L of y2 of x is 0, so this just becomes c1 times 0 plus c2 times 0, which equals 0. So what we have seen then is that if these two functions y1 and y2, when you apply L to them, give you 0, then any linear combination of these, L of that linear combination is also 0. So since we're talking specifically about differential equations in this case, we can say that if y1 of x and y2 of x are solutions to L of y of x equals 0, then this linear combination of those two functions is also a solution to L of y equals 0, no matter what values the constants c1 and c2 have. So let's go back to that problem we had before. Same differential equation as before. And now we want to find more solutions to that differential equation, more than just two. And as we'll see, it will turn out to be an infinite number of solutions. So far, we know that e to the half x and e to the minus x are solutions to this differential equation. So we've already found two solutions. But this is a linear homogeneous differential equation. So by that superposition principle that we just saw, if I take any linear combination of these two, such as c1 e to the half x plus c2 e to the minus x, where c1 and c2 are constants, this function, call it y of x, is also a solution to that ordinary differential equation. So at this stage, I can pick c1 and c2 to be any numbers whatsoever. There are an infinite number of choices for c1 and c2, so that gives us an infinite number of solutions to this differential equation. So we already have now an infinite number of solutions before us. And then the question is, are these all the solutions? Are there more solutions to this differential equation than are shown right here? And it turns out that the answer to this question, are these all the solutions, is yes. This formula up here represents all the solutions to this ordinary differential equation. And because of that, since this is a formula that gives us all the solutions, we call that the general solution to this differential equation up here. Our goal in general is to find general solutions. So far, we have found two solutions to that previous differential equation, and by taking superpositions, we got an infinite number of solutions, and we need to tackle the question, how do we know that we found all the solutions? So we're going to have to look at a little bit of theory here. So first of all, let's talk about the linear independence of two functions. And let's call the two functions y sub 1 of x and y sub 2 of x. These two functions are linearly independent on an interval I, and we can think of it as an interval of x values, if and only if this only solution to the equation c1 y1 of x plus c2 y2 of x equals 0 for all x in I is that c1 is 0 and c2 is 0. If we look at the case where both of these are 0 and put a 0 in here and a 0 in here, 0 times y1 plus 0 times y2 is obviously the 0 function, and 0y1 plus 0y2 is called the trivial linear combination, or the trivial solution if we're talking about a homogeneous differential equation. So in any case, this looks a little bit weird when you first look at it, unusual. What does this mean? Well, for two functions, let's look at what it would mean if they are not linearly independent. Two functions, y1 of x and y2 of x, are linearly dependent on an interval I if one of the functions is a multiple of the other. Okay? Now, if you look up here, for instance, suppose we subtracted this quantity, this term, from both sides of this equation. We would then have that c1y1 equals minus c2y2. And if we divided through by c1, we would get that 1y1 of x is going to equal, on this other side, c2 divided by c1 times y2 of x. In other words, just solve this equation for y1 of x. And you might say, oh, okay, that's nice. But then I might say, well, what if this c1 were 0? Then you couldn't divide through by c1 to find out what y1 of x is. But if they're linearly independent vector functions, then one of these has to be non-zero. If c1 is not 0, we can get y1 in terms of y2. y1 will be some multiple of y2. If c2 is not 0, then we could solve for y2 as being a multiple of y1 by just some simple, middle school algebra. So let's look at an example of linear independence. Let's show that these two functions are linearly independent on minus infinity to infinity. The function e to the half x and the function e to the minus x. If you remember, these were the two solutions that we found for that homogeneous differential equation we saw just a short time ago. So what we need to do is suppose that c1 e to the half x plus c2 times e to the minus x is 0 for all x in minus infinity infinity. And we have to show from that c1 and c2 have to be 0 constants. If this is identically the 0 function on this interval, then these two constants both have to be 0. Okay, well, let's see. If this equation holds for all x, it has to hold for x equals 0, which would be c1 e to the 0 plus c2 e to the 0 equals 0. So for this equation holding for x equals 0, we get c1 e to the 0 plus c2 e to the 0 is 0, but e to the 0, remember, is 1. And so this is just c1 times 1 plus c2 times 1. And so this equation simplifies to c1 plus c2 equals 0. Well, once again, if this equation holds for all x, it has to hold for x equals 1. So if we plug x equals 1 into this, we get c1 e to the half x, e to the half, a half times 1, plus C2 e to the minus 1. And so that also has to equal 0. So we have two equations here. C1 plus C2 has to equal 0, and this combination of C1, C2 also has to equal 0. Having these two equations both equaling 0, is that enough to show that C1 is 0 and C2 is 0? Well, let's find out. So far, we know that C sub 1 plus C sub 2 equals 0, and C sub 1 e to the half plus C sub 2 e to the minus 1 equals 0. So let's multiply this first equation, both sides, by e to the half, and leave the second equation the way it is, and then we'll subtract the two equations. So the first equation becomes C1 e to the half plus C2 e to the half equals 0 times e to the half, which is still 0. The second equation remains unchanged. Now let's subtract. If we look at these two terms, C1 e to the half minus C1 e to the half is 0. C2 e to the half minus C2 e to the minus 1 is C2 times the quantity e to the half minus e to the minus 1, and that equals 0 minus 0, which is 0. Now look at this second equation. We know that e to the half minus e to the minus 1 power is a non-zero number. So we have C2 times a non-zero number equals 0. So that forces C2 to be 0. We must have that C2 equals 0. But then, looking at the first equation, C1 plus C2 equals 0, and remembering that C2 equals 0, this is just the equation C sub 1 plus 0 equals 0, which gives us C sub 1 equals 0. And so, with the argument that started on the previous slide, we have shown that the two functions that we started with are linearly independent. Okay, we're about halfway to showing that we actually did have a general solution to that constant coefficient linear homogeneous differential equation that we looked at before. But I'm still trying to show that that linear combination C1y1 plus C2y2 actually was the general solution. It actually turns out that we can even go to just second order homogeneous linear differential equations in general and show what all the solutions have to look like. In other words, find the general solution, know what the general solution looks like. So we're going to generalize just a little bit now, I guess, to this differential equation. The second derivative of y with respect to x plus p of x times the first derivative of y with respect to x plus q of x times y equals 0. And here's a fact which we're not going to prove, but we will be using quite a bit. If p of x and q of x are both continuous on an interval I, and suppose a is a number in that interval I, and suppose that y0 and y1 are numbers, then this initial value problem over here, this differential equation, homogeneous differential equation, with initial conditions y of a equals y0, y prime of a equals y sub 1, that has a unique solution. So it has a solution, and there's one and only one solution to this initial value problem. That's going to be important when we want to conclude later that we have a general solution, and we'll see why. But first, let's look at a special case of this. Suppose I have this homogeneous linear differential equation, same one that we had up here, but the initial conditions, the y0 and the y sub 1, let's just suppose that they're both 0, okay? Well, if you think about it for a minute, can I think of a function that satisfies all three of these conditions? How about the zero function? If y of x is 0 for all x, then its first derivative is 0, its second derivative is 0, and in that case, for the zero function, these three terms will just be 0 plus 0 plus 0, and yep, that equals 0. Does the zero function evaluated at a equal 0? Yes. Does the derivative of y evaluated at 0 at a equal 0 if y was the zero function? Yeah, because the derivative of the zero function is still the zero function. Evaluate at a, any number a, and you still get 0. So the only solution to this particular initial value problem is the zero function. No other functions satisfy this initial value problem. Here's an important fact. We're going to be looking at two initial value problems with the same differential equation, homogeneous linear differential equation, here and here, the same, but the initial conditions are different. y1 of a equals 1, y1 prime of a equals 0, and down here, y2 of a equals 0, y2 prime of a equals 1. Notice here we have 1 and 0. Down here we have 0 and 1. They're flipped. So let's suppose that in this differential equation we are considering an interval I, and we're considering a number a for these initial conditions that is in that interval I. Suppose that the two functions that appear here as coefficients, p of x and q of x, are both continuous on I. Then, if you let y sub 1 of x be a solution to this initial value problem, and y2 of x be a solution to this initial value problem, then it turns out that these two functions, y1 of x and y2 of x, are linearly independent on I. So this is important because if we have two linearly independent solutions to this same differential equation, different initial conditions obviously, then these two linearly independent solutions can be used to find the general solution, which will just be an arbitrary linear combination of these two functions. Okay, so let's see. We have that y1 satisfies this initial value problem, and y2 satisfies this initial value problem. And we're trying to show that y1 and y2 are linearly independent. So let's suppose that we take a linear combination of y1 and y2, c1y1 plus c2y2, and we set it equal to 0. And what we would have to do is show that c1 and c2 have to both be 0. So let's call this linear combination of y1 and y2, let's call it y sub s. So in that case, since y sub s is a linear combination of these two solutions to this kind of differential equation up here, y sub s also satisfies that differential equation. So the second derivative of y sub s with respect to x plus p of x times the derivative of y sub s with respect to x plus q of x times y sub s has to equal 0 for all x. Let's look at y sub s of a. According to the way we defined y sub s of a has to be c1 y sub 1 of a plus c2 y sub 2 of a, and in this case we know that y sub 1 of a was 1, y sub 2 of a is 0, so this is just c1 times 1 plus c2 times 0, and that is c1. Now let's look at y sub s prime of a. that is going to be, according to what y sub s is up here, c1 y sub 1 prime of 0 plus c2 y sub 2 prime of 0. But y sub 1 prime of 0 is 0. Y sub 2 prime of 0, sorry, y sub 2 prime of a is 1. Let me just say that again. This is going to be c1 times y sub 1 prime of a, which is c1 times 0, plus c2 y sub 2 prime of a, which is c2 times 1, which is just c2. So what we have then is that y sub s of a is c1 and y sub s prime of a is c2. But y sub s is the zero function. So we must have that y sub s of a is 0 and y sub s prime of a is 0. The zero function evaluated at a and the derivative of the zero function evaluated at a have to be 0. Differentiate a zero function, a function that's 0 for all x, you just get 0 back. So let's see. Here we have y sub s of a is c1. Here we have y sub s of a is 0. So that must mean that c1 was 0. We also have that y sub s prime of a was c2, but y sub s prime of a equals 0. So that forces c2 to equal 0. So by assuming that this linear combination of y1 and y2 was 0, we just ended up showing that those constants c1 and c2 both had to be 0. And that tells us that y sub 1 and y sub 2 are independent. Okay, so we have now shown that these two solutions to this one differential equation, basically with different initial conditions, these give us two linearly independent functions, y sub 1 of x and y sub 2 of x. Now here's the next fact that we're going to need. If the functions y sub 1 of x and y sub 2 of x are solutions to this differential equation, then the general solution to the differential equation is c1 y1 of x plus c2 y2 of x. Let's see why this is true. Okay, we're still looking at two functions, y sub 1, y sub 2, that satisfy these two initial value problems. And here's a fact that we're going to show. Let's let B be the set with the two functions y sub 1 and y sub 2 of x. That set of functions spans the solution space to this differential equation. That is, every solution of the ordinary differential equation, this one here, can be written as a linear combination of y1 and y2. So let's see why that's true. Let's suppose that y sub x is a solution to this differential equation, and if we have a function y that satisfies this, plug a into that, and whatever y of a is, call that number c1. Also, plug a into your function y prime that you have that satisfies this equation, call that number c2. So in other words, this y of x that we're talking about right here is a solution to this initial value problem. This function satisfies this differential equation, this homogeneous differential equation, and y of a is c1, y prime of a is c2. Okay? But wait a minute. Suppose I look at another function, which I'm going to call y sub s, and let it be c1y1 plus c2y2. Then y sub s satisfies this same initial value problem that y did up here. This is a linear combination of y1 and y2, which are solutions to the differential equation that we have up here. And so y sub s does satisfy that differential equation by the superposition principle. And we also have that y sub s of a is C1, y sub s prime of a is C2. So we have a function y satisfying this initial value problem. We have y sub s, which is C1, y1 plus C2, y2, satisfying the same initial value problem. That must mean that this y that we have up here is equal to C1, y1 plus C2, y2. So what we have done was we have arbitrarily picked any solution to this differential equation, and we have shown that we can write that particular solution as a linear combination of y1 and y2. And that means that these two vectors, this set of vectors, spans the solution space for this homogeneous linear second order differential equation. Any solution to this differential equation is going to turn out to be some linear combination of y1 and y2. Now, we're going to say something more about the general solution of this differential equation. It turns out, and we're not going to prove it, that if you have any two functions, y sub 1 and y sub 2, that are solutions to this differential equation up here, and they're linearly independent, then the general solution can be written as y of x equals c1 y1 of x plus c2 y2 of x. Here I'm not saying that y1 and y2 have to be those two functions that were solutions to those two initial value problems we saw earlier. They could just be any two functions that are linearly independent, and both of these functions solve this differential equation. So you can generate all the solutions to this differential equation up here by looking at linear combinations of two linearly independent solutions. If we had time and if we were taking stock of some properties that are proven in a linear algebra course, we would find out that this set of solutions to this ordinary differential equation up here is a vector space of dimension 2, and thus any two linearly independent vectors in this solution space will span the solution space. So when we have a second order linear homogeneous ordinary differential equation to solve, all we have to do is find two linearly independent solutions, and then we can use those two solutions to write down a formula for the general solution to that differential equation. So I'm going to reiterate what we just said, but I'm going to do it in particular for the constant coefficient problems that we are going to be looking at. So I'm going to look at a constant coefficient homogeneous linear differential equation, a times the second derivative of y with respect to x plus b times the first derivative plus c times y equals 0, a, b, and c being constants. The solution space of this homogeneous differential equation is a two-dimensional vector space. If you can find two vectors or two functions, y1 of x and y sub 2 of x, any two linearly independent solutions to this differential equation, then the general solution to the differential equation can be written as an arbitrary linear combination of y1 and y2. So this formula gives us all the solutions to that constant coefficient linear ordinary differential equation. When you write down a general solution like this, we have to remember that at this stage we're considering C1 and C2 to be arbitrary. we can pick C1 and C2 to be any numbers we want, and that will give us a solution to this differential equation. If we pick C1 and C2 to be two different numbers, then we get another solution to this differential equation. By letting C1 and C2 run over all numbers, real numbers or complex numbers, we would get all the solutions to this differential equation. So let's look at an application. Let's solve this initial value problem. 2 times the second derivative of y with respect to x plus the derivative of y with respect to x minus y equals 0. Y of 0 equals 2. Y prime of 0 equals 3. Okay, well, we already found the general solution to this differential equation earlier in this lesson. And the general solution was c1 e to the half x plus c2 e to the minus x. So all we have to do at this stage, since we've already found the general solution to this differential equation, is to figure out what values of c1 and c2 we need in order to satisfy these initial conditions. Okay, well, first of all, if y of x is this, plug in 0 for the x. And we get y of 0 is c1 e to the 0 plus c2 e to the 0, and that's c1 plus c2. Okay, so we're interested in y of 0 equaling 2, so eventually we're going to set c1 plus c2, which is y of 0, equal to 2. Okay, now what about this initial condition y prime of 0 equals 3? Well, what we have to do first of all is start with this formula for y of x and differentiate it to get y prime of x. When we differentiate it using the chain rule when necessary, y prime of x is a half c1 e to the half x minus c2 e to the minus x. Now if we plug in 0 for the x in this, we get y prime of 0 is 1 half c1 e to the 0 minus c2 e to the 0, and that just turns out to be 1 half c1 minus c2. So this first initial condition tells us that this stuff has to be 2. This second initial condition tells us that this stuff has to equal 3. So here we have a system of linear algebraic equations. We know how to solve them. I'll skip going through the steps of the solution to these. It turns out that C1 is 10/3 and C sub 2 is minus 4/3. So then we can substitute these back into this general solution formula, and so we'll have 10/3 e to the half x minus 4/3 e to the minus x, and that, which we have written down here also, will solve this problem. It satisfies this differential equation, and it also satisfies these initial conditions. So to summarize, we defined the order of a differential equation. So now if we look at a differential equation, we can see what its order is. We can compute it. We discussed various forms for the second order linear differential equation. We defined homogeneous and non-homogeneous systems. We started to find solutions to constant coefficient homogeneous linear differential equations by looking for exponential solutions. We covered one case where the characteristic equation, which was a quadratic equation, had two distinct real solutions. We also learned that for second order linear homogeneous ordinary differential equations, the solution space is two-dimensional. It's generated by any two linearly independent solutions to the ordinary differential equation. And then we solved a problem where we found the general solution to an ordinary differential equation and also the unique solution to an initial value problem. I hope that you enjoyed this lesson. I hope you continue watching the others. Thank you for your attention. I would like to thank you for watching this video. I hope you have found it to be an enjoyable learning experience. If you're interested in ordinary differential equations, there are additional videos in this series covering most of the topics in an introductory course in ODEs. Have a good day.